Okay, so recently I've been working on a addition device. I don't get really angry. An addition device, which sort of works similar to a computer does, but slightly different. So the way I'm building it is a computer would use transistors, which I have no clue how to wire. So instead I'm using a relay. So this is a, I think it's what, single pole dual terminal. So these two terminals here, if you want the switch inside the relay to change, you put current through these two terminals, and then this terminal, and I think it's this terminal, is normally closed. So if you don't put a current through these two, then these two terminals here will be completing the circuit, and these two terminals won't. But if you put a current through the here, then these two terminals will complete the circuit and this terminal won't. And that's what I'm using as the basis for logic. So I'm going to show some components and sort of explain how they're going to work. Okay, so this is an OR gate that I've made. This side connects to the negative terminal of the battery, and this side connects to the positive terminal. And because to save on the amount of batteries you're going to need, I'm going to be connecting all the circuits in parallel. I've put a LED here to prevent backflow and also show me what the state of the OR gate is for future debugging. So the way it works is at the positive terminal, I've soldered the two wires together so that it will split into the two relays, and the inputs for the OR gate will be the terminals on here, and I've standardized it so the inputs are integrated into the circuit and the outputs will be just 3 wires. Right, so I'll separate these a little bit. And what I've done is it will split, and then if there's a current running through this one, then this switch will close, completing the circuit, which means there will be a current flowing through the LED. And if this switch closes by a current flowing through, then the current will flow through the LED. But if none of them close, then the circuit will be open and the LED won't turn on, which is an OR gate. Because if one of them is on, or the other, or both is on, then the LED will turn on, otherwise it won't. This is an AND gate, and the way it works is, if I show you the inside, again we have an LED, negative side, positive side, and this time the way it works is instead of the OR gates, which are effectively in parallel, what I've done here is so that they're in series, so that if this one's closed but this one's open, the circuit won't be closed and the LED won't be able to turn on. They both need to be closed for the LED to turn on, which is an AND gate. Okay, so now I've shown an OR gate and an AND gate, but I haven't actually shown any of them working. So I'm gonna show building an inverter and it working, which will be pretty hard considering one hand needs to be holding the camera. But so here's the battery. I'll turn it off for the time being, safety. And I made one before, but dismantle it. And yeah, as you can see, this isn't even all the wire clippings, because we have 7 AND gates, 3 OR gates, and so far 4 XOR gates. So I need to make 3 more before I can start final construction. But it does take a while. Let me move the soldering iron out of the way. The iron's off, by the way. Yeah. And so how am I going to do this? So what we want is, first of all, we're going to connect it to a relay, which is over here. and there. We're going to connect them to the LED through the relay. So this is going to connect to this terminal here. Also, because this is that temporary demonstration thing, because inverters aren't necessarily needed in the final construction, I'm making them with crocodile clips instead of soldering them on with wire. There. And close that. No, I'm gonna do it with my right hand. There. Wait, give me a second. Okay, so now with the use of both hands, I've successfully connected the bulb through the relay here to the battery, and that's slanted, isn't it? I can fix that, yeah. There. I've successfully connected the battery to the bulb through the relay. And now we can see, because of the terminal I've connected it on, if the battery's turned on, then the bulb turns on. If the battery's turned off, the bulb turns off. Now this is a normal bulb circuit. You could probably do it much more simply than something like this. But the advantage of a relay is that now, if I connect these two terminals up with a switch, then I'll have a little bit more freedom in what I can do. So I'm gonna do that. Okay, so I have to get a bit clever here because I have a lack of crocodile clips and wires. But now we have it all wired up with the two terminals connected as well. I had to get a little bit clever here as well, so that I could make the line split. Sorry. But now, as you can see, if I turn the battery on, the bulb turns on here, even though the switch that we have here is off. If 0 is down, it's off. If 1's down, it's on. Right? And that was just my finger moving the wire. Turned it off. But now, if I turn the switch on, so that 1's down, so it's on, as you can see, the light bulb there turns off. And if I switch the wire, if I switch, it turns on. Switch, it turns off. So now when the switch is on, the light bulb is off. And when the switch is off, the light bulb is on. And that is the essence of an inverter. Now, if instead of a bulb here, instead of an LED, sorry, here, you had a different relay, then you could feed the output of that relay, because the relay is essentially a switch. So you could feed the output of that relay into a different logic gate, which I can't do here because these are all the crocodile clips I have for temporary. But later on I'll update when I finish this and connect it all to the battery. No guarantees that it works though. But yeah, that's the basics behind the relay logic. I'll turn it off. That's the basics behind this relay logic. And I haven't explained how the XOR gate works yet, so I'll do that now. So this is the XOR gate, which, all things considered, is a big mess. But, oh, wait, am I holding it upside down? Never mind, it's facing downwards, so there's no upside down. But, so it's a big mess. I'll accept that. But the way it works is sort of simple. So I'll do a quick explanation first on how it works, on the Boolean algebra behind why it works, and then to the implementation of it into relays. Okay, so let's say you want an XOR gate, and an XOR gate is pretty hard to do if you think about it, because for an AND gate, we're going to look at something called the truth table. So for an AND gate, you have two inputs, so in 1, in 2, and you have one output. right? And in1 could be 0, 0, 0, 1, 1, 0, 1, 1, right? Now the output is 0 everywhere except for if both of them, right? So then you could have two things in a chain where something will happen only if those two things will happen, as seen in the relay example, where you have two relays in a chain, and you need both of these to have current in order for current to flow through the whole thing, right? Now for an OR gate, again you have the truth table in 1, in 2, and output, and then again, and now it's a case of 0, then everything else is 1, right? And you can sort of view that as if something happens or something else happens, then something else will happen, which we can see in the OR gate. So if this relay gets current or this relay gets current, then current will flow through the whole thing. It doesn't matter if both of them have current, because then current will still flow through, right? And an XOR gate is much harder to do, really, but is also a big necessity when it comes to digital logic, which is essentially what I'm recreating here. So an XOR gate, so XOR stands for exclusive OR, and again we have in 1, in 2, and output, right? And then again we have our standard options. Now we have 0, then we have 1, 1, but then we have 0 as well. So you can view that as if the inputs are different, then the output will go, right? But then this is a lot harder because now every input will depend on the other input if it has an output, right? Because now if the first input 0, then the output will be just the input 2. But the first input's 1, then the output will be the inverted input 2, right? And that's really hard to implement. So a way to, how do I explain this? So a simpler, I say simpler, but a more generalized way, I should say, of doing it could be, well, okay, so we know how to make it so that only one input we know how to make it so that only one input allows for something to happen, and that's an AND gate, right? And we know how to make it so that multiple inputs can cause something, and that's an OR gate, isn't it? So we can actually use combinations of AND gates and OR gates along with smart inputs of inverters to create an XOR gate. So I'm going to explain how that works now. So if we rub this out, now let's think about it. If we have an OR gate and we want them to be different, let's make AND gates so that if they're different in one way, then it will cause an output. Then we make another one, so if they're different in a different way, it will cause an output, right? So for AND, I'm going to use multiplication. For OR, I'm going to use addition. And I'm going to use a bar on top to signify inverted, right? So let's see, if we have, I'm going to say A and B instead of input 1 and input 2. If we have A and not of B, now what's that equal to? Well, if A is 1 and B is 0, then not of B will be 1, A is 1, not of B is 1, so if we AND them, that's going to equal 1. And in any other scenario, that's going to equal 0, right? So now, if we have not of A and B, then it's the same thing, it's symmetric, but the other way around. So now if A is 0 and B is 1, then this is going to equal 1, isn't it? So now we have the individually, we have when it should equal 1. Now, how do we make it so that these two are in one complete system? Well, it's pretty simple to do that. Because these don't overlap, then we could actually say the A times not of B, and then we could OR that to not of A times B, right? Because now let's think about it, because if A is 1 and B is 0, then this is going to be 1, and this is going to be 1. And this doesn't matter, because we know that if this is 1, then this is going to be 0, right? Which means that the OR is going to equal 1. But if A is 0 and B is 1, then not of A is going to be 1, and B is going to be 1. And we know that that doesn't fulfill this gate, right? So, if we OR these together, then we'll still get a 1. And for any other combination, which is just 0, 0, and 0, 1. So, this is how I'm using relays to recreate digital logic. If you enjoyed, then in the future I'll make a video of the final thing working and completed.